Welcome to this webinar on the AlphaZero algorithm, the lesson on AlphaZero algorithm. So let's get started. So why are we using this AlphaZero algorithm in the first place? Why was it invented by the team at Google's DeepMind? So if you have seen the professional human players play uh, board games like chess or Go or even tic-tac-toe, uh, more for Go and chess. So for those games, these human players, they they do some calculations for before making their next step, before taking their next action, given their current situation. They do some calculation in the future, and based on that, and their intuition from their experience from playing these games for a long time, based on uh, these two components, they decide which action is the best given their current situation. So that's what we are trying to imitate here in the AlphaZero algorithm. We will have this Monte Carlo tree search model to to do all the calculations about actions, which action is the best, and they will help us decide which action is the best. And they will be guided by deep neural networks. So the deep neural network is going to work as the intuition here. Now, professional human players, they built their intuition by their experience, by playing a lot of games, and it's all in their brain. They have seen uh, what is the best action to take given current situation. That's what deep neural network here is going to store. We will do many iterations of the game, and from beginning to end, and the deep neural networks will learn from those iterations, from their experiences, and they will store the knowledge that they learned from it. They will store the what action was best, so they represent, so deep neural networks will represent the intuition built from a lot of experience. Okay, so let's first take a look at this Monte Carlo tree search model, what it does and how it works. And then we will introduce how to use deep neural networks with them. Okay, so AlphaZero algorithm specializes in zero-sum games. Uh, by that, I mean that one agent's win is other agent's complete loss. Okay, and there are two competing agents trying to win games against each other. So it's an adversarial game, one against the other, and there is a long-term strategy involved. It is not a reflexive action game. For example, you might have seen in TQN algorithm, or the navigation project, or the tennis project. The actions taken by those agents were reflexive. So given this state, what is my best possible action? Just thinking about this state. Well, even then, we did an estimate of the total score from by taking this action, but we didn't actually have a model to predict that final score. We relied on just another neural network to predict that final score for us. But here we have a model called the Monte Carlo tree search that will help us get better estimates of the final score for our neural network. And also, there is no hidden information in this zero-sum game. So that's more important here, these 3 points. And these are the examples of zero-sum games. So there is a tic-tac-toe game, the simplest, chess, and then even more complicated is the Go game of Go. Okay, so let's take a look at a random tree walk, like an example of a tree walk. Suppose uh, I get this state. So player one is the circle, and uh, This is the first step taken by player one. Then the player two has to decide which action to take. Player two has, let's call x and a 0. So x has uh, uh, 5, 1, 2, 3, 4, 5, 6, 8 possible actions here. Sorry about that. So player x has 8 possible actions that it can take, and so on and so on. But before just randomly taking any action, the player has to think about the future. So the player's x thinks that, okay, if I take this action, circle will take this action, sorry, this action, and then I will take this action, and then circle will take this action, and so on and so on. And the player x predicts that uh, circle will win. So for player x, taking this action wasn't beneficial. So this is an example of the tree walk. So both players at each point in time do this future calculations and decide which action is the best for them, which gives the best outcome. And yeah, this the same thing can be represented mathematically. So circle is has +1, and x is represented by -1, and the empty ones are represented by 0. So this is just a matrix, 3 by 3 matrix with these values, and these values +1, -1 uh, aren't the scores. Okay, we do have score here as +1, but it happens in the end. These are just representative of what action each player took, and so we put -1 where x would have been, and +1 where circle would have been. This is for us. This is for us when we compute, when we write the program. So it's just a matrix. Okay, and if circle wins or the blue player wins, the final score is +1, and if the other player wins, x wins, the final score will be -1. And so from the perspective of the blue player, score of -1 will be a bad thing, but from the perspective of the orange player, the x score of -1 will be a good thing. So uh, when we train our networks, we we play against ourselves. Okay, and so at that time it will be useful to remember this action, that whenever we compute a score given an action, it's from the perspective of that player. Okay, but we will see that in more detail. Okay, so how to represent it in the form of reinforcement learning? So board game and a particular state is st at time t, and the player's action is represented by -1 to the power t. So since we are doing self-playing, we are not playing against the environment. We want to train our network by by assuming the role of both players one by one at each time step. Why are we doing this? Because this will help us learn faster instead of um, spending too much on having too many iterations, because computation is expensive. So this way we will learn twice faster. So yeah, so for player one, its action is represented by +1, uh, and so so this at time t equal to 0, this value will be 1. So we are assuming that the blue player is the first player to start, and it takes action 0. It takes A0, and the orange player takes action A1. So when this is 1, this will be just -1. So we are saying that whenever there are even actions, So even actions, it's going to be a player one's action, and whenever there are odd actions, that it's going to be the orange player's action, odd. And also player one's goal, sorry, the blue player's goal is to maximize Z, whereas the orange player's goal is to maximize minus Z. So we are looking at it from the perspective of the player, right? Minus Z. Okay. So again, I'll explain this. So we use one uh, policy network, one neural network to compute policy for both agents, and one critic network to compute the action value, the V, for both agents. But since we are doing a self-play, we have to alter this. So this makes it from the perspective of the player. This changes it to the perspective of the player. Okay. Okay. So as I said, so given this state, okay, so circle, then X, then circle. Now it's X's chance to select an action, and it has six possible moves, and even after that, after each move, there are many possible moves that circle can take, and even after that, there are many possible moves that X will take, and that is only for one state and one action. So for each of these action, there are many possibilities of actions that each of those players can take one by one. So this becomes very computationally expensive. That's the point of showing this slide. And you want to, in the end, you want to compute the score, and based on that score, you want to decide which action is the best. So using brute force is going to be very expensive. Brute force is what I said previously, that for taking each action, compute the final score. But now I if I take this action for X, I want to compute the final score. But even for subsequent actions, I will be computing the final score for both players each actions. So since you only see one branch coming from this action, there will be many branches because there are many possibilities. And same goes for other branches, and same goes for all these different states before this state, because this is not the first state. So using brute force will take a lot of time, and it will be very expensive, right? And that only for taking one action. So yeah, it's really very expensive. So what we need to do when we predict the best action for X is to uh, branch out. So given this is the situation for X and it wants to select an action, so let's branch out by only one step, and then try to predict the outcome of the game from here for each action. So instead of using brute force and going all the way for just one action, we will be using predictions. And we also need to explore so that we don't miss any better action. We can't use greedy actions. So for all this, we will be using Monte Carlo research method. So let's take a detailed look at it. Okay, so let's first take a look at the notations used. So there's a U, N, and V. Uh, V is the expected score given this state. Okay, so this is the first state. Sorry, this is the state X has been provided with. There have been many previous steps, but we are starting from somewhere in the middle. So first, let's say circle took one step previously, and then X took one step, and then circle took another step, and then now it's X's turn to select one of the actions. So, and we want to predict, right? I just said we want to predict which action will be better. So for that, let's say X takes this action. So what V is what will the final output of the game given this state, given this action? What will be the final output of the game if this state happens? That is, the circles are here, X is here, and the next X is here. What will the final game output? Same goes for each of these states. So V computes the final score of the game or final output of the game. N is the visit count to that state. How many times this state was visited during our iteration? Because we are going to iterate, we won't be uh, selecting just one action and moving on. We will be, because we want to explore, we want to iterate as explore as many actions as possible. And so N stores how many times this state was visited or how many times this action was taken given this state. Same goes for this, and all this. So that's N. And they together make up U. So the first component, V, is for exploitation. So we want to select the action given this state, so, such that it has larger U. Okay. So the V part here, if it's more, is going to increase U. So that will control the exploitation. And the second part here controls exploration. So it makes sure more and more random states are visited. So if a particular state or particular action has been taken many times, this term will reduce U, forcing your tree search model to explore more. Because if this state keeps happening again and again, you will go down. So your model won't select this action too often. It will select something else which has higher U because of lower N. Okay. So U is the sum of this two, and N tot is how many times a complete game was played. So the next step, what happens after this is, suppose I now in the beginning it's all zero. So suppose I randomly select this action, I go to this state, and then I will randomly play the whole game. I will let the game end, uh, and I will randomly select the actions for circle and zero randomly. Okay, after this step, uh, and then I will let the game end. So when I say random, let play a random game after this step, that means after this step, I won't be using this tree search. I'll just randomly select, assign actions to the remaining blocks, and I will see who won. Okay. And so each time that whole random game is played until the end, my N tot increases to 1. So N tot is the number of times a total random game is played given this state. So since we are deciding next action for this state, we are computing N tot for this state. Okay. In the future, when you want to compute the next action for this state later using MCTS, not random gaming, using MCTS, each of these states will have their own N tot, but we will see that later. So N tot is only for this state because we are selecting next action given this state. And once we play a full random game, N tot is +1. And then we will select the action with larger U. So we will run iterations on this few times, and then we'll select the action with the larger U. Okay, so let's see how it happens. So this is initial. Okay, and then since all are zero, I randomly select this action. Okay, my matrix, since this is just a matrix, I get this, I put here. -1. Okay, so I got this action. Then I will run a whole random game. Okay, and let's say X lost in that random game. That means X got X final score from the perspective of X is -1. Okay, so it's going to be from the perspective of the player. Okay, since X lost it, this is -1. If X has won it, this would be +1. Okay. Uh, Again, eh, if came before this, if I started before this state, and if a circle, I had to choose the next step for circle, and if a circle had won that game, it would be v equals 1 over there. Okay, so this is from the perspective of the player. If it's if the player has lost after taking this action, v equals -1. And so n becomes 1 because I visited this state once, and then I compute my u as -0.5. Okay, and then I will run more iterations. So I will randomly, now u here is -0.5, so I won't be selecting this u because I have to select an action with higher u. Okay, and by the way, this become 1 as well using the same computation. So because of -1, this become -0.5, but others have v as 0 and n is also 0. So uh, it only, and n dot becomes 1, right? Because we played one whole random game. So the u for them becomes 1. So this is 0 and this term stays 1. 1 plus 0, root of 1 is 1. So u is 1 for this. So since their u is higher than u for this action won't be selected anymore. And it makes sense because it gave um, a loss to player X. Then again, randomly select and one action. And if you select any one action, play a complete random game until the end, and then update these values. Okay. So let's say I did 100 iterations. So I played 100 random games after selecting any one of these states. I mean, combined. So let's say I selected this a few times and I played uh, random games few times, and then I selected this and played random games few times. Total comes out to be 100 random games. Uh, yeah, and then how do I choose my best action after iteration? So int is 100 because I decided to do only 100 iterations. So it's up to you how many simulations you want to run. So I ran 100 simulations, I got this score, and I want to uh, decide finally that given this state, what is the best action. So I will look at u first. Now there are 3 actions which have same u. Then I will look at n, which has higher n, because I want to promote exploration as well. Exploration and exploration both are promoted. Choose the action with highest n. So this was for this state. Now there are some modifications done, that instead of just selecting action based on estimation of v, why not go one more step and then select action here. So it's like one step propagation, sorry, bootstrapping, like we saw in the actor critic method. So it will give us a better estimation of v and eventually a better estimation of u, right? So that's called expansion and backpropagation. So now this is a completely new state, and these are the initial scores. Okay, and now we will see how expansion and backpropagation works. So I have this initial this state, and this is my iteration. So I didn't run 100 iterations yet. I'm starting with expansion and backpropagation from the beginning. So suppose let's uh, take some steps back. So I started with this, n dot was 0. I randomly selected this action. Okay. And then I ran a random game again until the end. So don't think about this. Once I selected this action first, I ran a random game. Okay, and I updated my U here. Okay, since I won. Okay, so don't think of this yet for computing this. So I ran a random game and I won. So my V was 1, N was 1, and my U is 1 plus N dot is also 1 since I ran a random game complete for one time. So 1 plus zero point 0.5, that's 1.5. So this hasn't happened yet. After this, I selected this, ran a random game, updated this, N dot equals 1. Now I again go randomly, but since I have a U higher than all of these, now I will expand into this. Okay, so since if my U here had reduced to something lower than 1, like maybe zero point 0.5 or minus zero point 0.5 that happened last time, I wouldn't have gone and expanded after this. Since my U increased after taking a random game from here, I'm going to expand it into next step. Now, so this is an initial state for the next step. And then again, I will, and they will all have all these zeros in the beginning. Okay, U0, N0, V0. I will again select some state, some action randomly for the circle now, right? So I selected this X action for X, and the next action will be selected by circle. So given this state, I selected this action for circle randomly because initially all were 0. These numbers are updated, so ignore them. Initially they were all 0, 0, 0. Randomly I selected this, and I came to know that uh, circle has won now. After I selected this and played a random game until the end, I came to know that circle has won. So I gave this as 1, n is 1, and so because of these two, u is 1 for this, and n dot is 1 because I played one random game after this state, right? So the n dot, this n dot belongs to this state. This state should be in the center, and n dot belongs to that state. And after this, I have to update my previous actions. So expansion is what happened until now, until you update this, and back propagation is based on this new knowledge. I have to update this. So since v is 1 here, from the perspective of circle, this becomes 1 minus 1. So this becomes 0 from the perspective of x. So taking this action, what we are saying is taking this action led to a loss for x. So this becomes 0. And this becomes 2, and this will also be updated, and this will become 2 because uh, we played a random game through this node eventually, right? Right. So this became 2, this became 0, this became 2, uh, because we played a one full random game that originated from this uh, state. And this by calculation, this became 0.47. Okay, because root of 2 over 1 plus 2 3, and this is 0. So after calculation, this became 0.47, and number of n dot is 2. Now I see that I will compare my u's now. So this is less u, so I won't be again selecting this and expanding. I will go to some other state, 1.441414141. So any one, if this is less, so it won't be selected. Any one of these will be chosen, and then we will play a random game from there. There won't be expansion because there are multiple of these which are the same, right? And if in the future, uh, within those 100 iterations that I'm doing for this state, if within next simulations less than 100, if some of these have highest u compared to any of the actions, I will again expand and then back propagate and update it. So yeah, so you get, I hope you get the idea. So I will do that 100 times. And again, let me explain again, review it. You will only expand and back propagate if your u is highest. If your u is not highest, higher than anyone, if they are all equal, then you will just do a random game until the end and then update everything. Okay. And once you expand, you randomly select one of these and do a random game until the end. Update this, update this, update this, update this, and update this. And then again, run the rest of simulation. So we are selecting action X here, not the later ones here. We haven't come to that yet. Currently, we are running 100 total 100 simulations just to select an action X. Okay. So let's say after n dot equals 100, you have this scenario, 0.5 and everything. And yeah, this has already happened and this has been updated. And I got 0.55 and n as 21. I have other 0.55s, but since I'm done with 100, I'm going to stop here and select an action. And so I go by this because it has higher n, it has higher exploration and exploitation. Okay. And you can see here, there are more n dots here than one because this state was visited many times because maybe u was higher many times during this state. It could have been, if u was equal for all, this could have been visited randomly and then we just did a random game. But if u was highest for this as compared to others, we have done expansion and backpropagation of at least 20 times. Okay. So, and when n dot is 100, we have selected to take this as the action. Now we will, given this state, what action should we select? Then we repeat the same process for this state, same number of simulations until I get n dot as 100. I will do the same thing. And I can build up from here, by the way. So once I've selected this action, I have to move on to next action, but I've already done few simulations. So why should I start from scratch? I can start from this n dot as 20 and then use the same data and keep doing this until I reach n dot as 100 and so on and so on. Okay, so this is the summary. Initialize top node for current state, loop over actions for some n dot, how it was 100. Start from dot node, repeatedly pick the child node with the largest u if they are not all zero. If n is zero for a node, play a random game. Else expand node and play a random game from the randomly selected child. Uh, Update statistics, backpropagate, and update n and u as needed, and so on and so on. One addition should be here that if u is the highest, even then you can expand. Right. If n is zero, that means it has least u. In the beginning, there is least u, so you play a random game. If all u's are equal, then you select any one action and play a random game. But if any one u is higher, then you expand and play a random game from the selected child, and then you backpropagate and update everything. And yeah, and this is how you select the moves. And this is how a Monte Carlo tree search works without using any neural network. So we will be using we will be employing a neural network now. So what is so if you just use Monte Carlo tree search, it's fine for this kind of simple game of tic-tac-toe. But what if there is a large board game with so many possible moves? So for example, you can see here first move has first move in 361 possible moves, then 360 possible second moves, 359 possible third moves, um, and there are 50 million combinations of moves. So using Monte Carlo research will be very strenuous for each move, because here we had uh, after taking the first move you have 8 possible moves, but here we have 360 possible second moves, right? And the first possible move here were only 9, here it's 361. So it will take a lot of time to compute the V and N and the U, sorry, not N, but V and U for each move, and then for and so on and so on. So instead of just using the Monte Carlo research model, we will be using a neural network to help it and make the computation faster. And this is where the intuition builds in. So we are not just using a model, but we are adding some brains to it, which will store some intuition in it. So this is the Monte Carlo tree search MCTS guided by neural network. So I will explain all of these notations. So uh, by now you should know what a policy network is, that is the actor network, and what a critic network is, what it does. Actor network will give out an action given a state, and a critic network will estimate a action value given a state. So yeah, n is visit count, v is the expected score, and so this is how the u has changed. So v comes from here, from the critic control exploration. C is a hyperparameter that controls exploration. This is X for exploitation, excuse me. This for exploitation. C is a hyperparameter that controls exploration. This selects the action given this state. So what will be the next, uh, what will be the other agent's action given this state? So let's understand this well. So you are here, let's say, and you want to use this formula. So we will compute what is the score of the game, of the whole game, end game, given this state. So V depends on state. Uh, but but this term here will select what will be the other player action given this state. That's why it has -1 to the power t to get the perspective of other player here. So what is the other player's action at given this state st? So the circle, when circle chooses an action here, it's going to be at given st, right? So suppose if there were no agents, if there was just environment and one agent that's taking all the action, so you will say that, okay, I have this state now, what will be my next action? So that will be at, right? But in this case it's going to be action of the other player, so that's why at here, it's at, but it's from the perspective of other player. So just remember that this will give you actions of actions of the other player given I took this action. Okay, and so this will control uh, so yeah, hyperparameter that controls exploration. N dot is again for this state. 1 plus n is again for visiting this state how many times. So that's total u. And you want to select the max u, so that you select maximum u. That means you're selecting state which has high u and which has low n. So that means you are promoting exploration, right? If it has low n, that means it will have uh, this u overall will go up. So you are promoting exploration here, and it's guided by a network. So this is predicting the actions of agent uh, given this state. So it's predicting the action of circle given this state, and this will be useful later. You'll see. Okay, let's see how this works in a few seconds. Okay, so let's start from the beginning. So n is the visit count, v is the expected score, uh, estimated by the critic network. Okay, and u has this formula. So at first, x has to select its next action. N dot is 0. That is, I haven't started my simulation yet. So in the beginning, all are 0, 0, 0, 0, 0, and this will also be 0. Then I randomly select this action. So I put x here. Now my uh, critic, now it has random parameters. Okay, the network has random weights. It's not trained, it's not updated, nothing. It has some random initial weights. So given those random initial weights, using those and given this state, what will be the v? It will just randomly generate some x, some v that will go here. And again, my policy network actor is also has random weights. And so given this state, what will be the next action for the second player? That will be generated here uh, by the by the network. Uh, and number of visits here now will be 1, and n dot here will be 1. And then we will compute this, and we get this u as v theta plus c, this pi theta over 2, 1 plus 1, 2. Now, previously we used to do a random walk, a random game, and then we used to see who won, and then we used to decide v. Here we are not doing a random game now. We are just using our network to generate this v theta for us. So that's the difference here, instead of doing the random game. Okay, excuse me for a second. Right, so n dot will be 1, and we got this. Right. Now I'll again look through the values of, and also u will be c pi theta here, because n will be 0 for them, n dot is still 1, so it will be c pi theta. V is 0, v is going to be 0 for them, because yeah, for obvious reasons, it was the state wasn't visited, so v is 0. So these all become c pi theta. This we saw already. N dot is 1. Now my algorithm will again look through, will again compare the u's, and suppose this u is smaller than this, because I have random weights. They are not updated, they are not trained, it's just random weights. So maybe v theta was -1, who knows. It's just random. So and maybe these end up being higher. So then my algorithm will randomly select one of these u's, and therefore it will select one of the actions x here. And again, the same thing, instead of doing the random game and etc., just use v theta given this state, and then select next player's action given this, add them up, and then you get u. So that, and then n dot is going to be 2 here. So n dot is 2. uh, okay, we ended up selecting this randomly. So this is a v theta given this state. It's important to remember that, because this is also called v theta, but it's going to be different than this because the input states are different. So this is v theta given this state, and then pi theta will also be different between, because it will be the action taken by circle given this state. So again, we get a u, n for this is 1, we get this, and n dot becomes 2. Okay, so now we can we know the basic how the networks are used. Now we will introduce the expansion and backpropagation in this. So this is the expansion part. Okay, so as previously I said, uh, I do uh, I do those previous two steps, and then I compare the u's, and then I find out, okay, maybe u is higher here. The u is higher here than as compared to the other ones now. And by the way, this will also change now. Pi theta root 2. These become pi theta root 2, because we are adding the v is 0 for this, for the other states. I'm saying the v is 0 for other states. The c is the same. Uh, theta t here will be from here, and this becomes 2, and this is still 0 for them, so it's root 2. So it becomes c pi theta root 2. That's the updated u for these states, right? C pi theta. Okay, so we have replaced this c pi theta that was previously we had with c pi theta root 2, the new. So we are not adding to the previous value of u. We are just replacing it with new values based on what action was selected. Okay, and then I find out that all these are less than this u. And n is 0. And also this will also change. This will also be same as this one, because they both have one n. Yeah. So these become new c pi theta root 2, and because this has n as 1, it becomes root 2 over 2, and the pi theta is the new pi theta now, right? Right. So it's important to remember this computation. We don't add up to the previous u. We just keep updating the u based on what your value of n is, and what your value of current v is. Uh, yeah. What is the value of v? The new value of v. It should be new value of v. Yeah. Yes. And since we didn't update v's here, they still remain 0. This one, so we won't be changing this v. So that means this v theta is not same as this v theta. So this remains the same. But when we but when we update this u for this one, this v theta is this v theta, this v theta is this v theta, but this pi theta is this pi theta, I guess, because it has to be given this state. Uh, no, actually, yeah, this pi theta is going to be given this state. Yeah. So let me, sorry for the confusion. I will clear it. So when we compute u, it depends on your v and your value of pi theta and your value of n. So here, since v is 0 and there was no previous action, n is 0, and there was no other pi theta selected as well because n was 0. So you use the pi theta that you get here. But after this, suppose you have n as 1, so it goes here. Uh, you had a previous v theta that you will use that, and you had a previous pi theta as well when you took this action, so you use that. So this v theta plus c pi theta root 2 by 2 will be representative of this taking this state. This v theta given this state, pi theta given this state. This is for this state. If you haven't taken any action before, then you will use this pi theta 2 here, pi theta. Okay, then I compare my u's and I say that okay, this is bigger than all of them. Then I will do expansion, and when I do the expansion, I will put this state in the middle. N dot is 0, and I will do the same operation once, uh, and then update, back propagate, and update these values. And again, I will compare the u's and so on and so on. So I did the expansion here, and dot is 2 still. Okay, so I compared and I saw this is bigger than all the rest. This is bigger than all the rest. I did expansion. I ran for however many times, because I ran this once. So it shows I here because okay, it's average. So I go here, I run it, I run the same loop, and then yeah, it's 1 plus. So this has to be updated as well. This end dot will also be updated. Yeah, whatever. So what here they are saying is that I saw this as max. I went inside and I run the loop again. I randomly select one action and run the loop again, and then I have to come back and update this after one loop. Okay, don't get confused by the I here. After any one action, I select one action, compute v, for that compute pi theta, update u, come back, and based on that v, I update my v, and I put a negative sign here because it's from the perspective of x. So if circle had 1 here plus 1, from perspective of x, it's a loss, so it will be a -1, right? That's why it's -1 here. Then if I run this one time, this I belongs to how many times I ran it, how many times I visited, and how many times I expanded. So if I expand one times, run one time, I add 1 to the number of states visited here. I update this as we saw previously, the same thing. And based on these two and the uh, pi theta that I got after this state, I update my u. And n dot has also been also be updated, and then again I run the same thing, and this I represents number of time I had to expand coming here. Okay, when you expand once from this state, you only run one action, you only find one action and then update, and then again look for better u. So that's for one state. Given one state, I have to run 100 100 n dots until I get n dot equals 100. I run, keep finding better action. Once I find a better action, by comparing U's, and if U's are same, then I compare n, which has highest n. I select the next action, and then I select the next action. So let's say I suppose selected this. Then I move on to the new one. So for the next one, this becomes the center, and the rest becomes the next actions. And I can, since I ran expanded a few times, I can use the same still same knowledge, and then I will select the next action given this action, one of those, and so on and so on. So we will see how the whole game works. So this is the first step. Then circle took one, X selected, right? So suppose X was presented this state, and it has to select one action. So given this state, uh, ntot was ran, for example, 100 times, and during those 100 simulations, uh, this state was visited, this state, many actions, sorry, many actions were taken, this action, this action, this action, and then U's were compared, and then if U was higher, then the expansion was done, back propagation was done, all that was done until n dot for this state was 100. After doing n dot equals 100, and 100 is just an example number. So after doing n dot, after we have n dot as 100, and then I compared U's for taking each action, and then I compared n if U's were same for multiple actions, and then I found that this has highest U, taking this action has highest U and highest n. So I selected this. Then I repeated the same process for taking next action and next action, next, until the end of the game. So I will do the same thing until the end of the game, the same process for each state. And then I will, and in the game, I will get the actual final score of the game, actual final score. Now this will be used to update our network. Remember that until now, we haven't updated the network. We are working with the same network with random weights, which is used to find policy and the action value. So we are using the same network without updating it, and we were waiting for. So using that network, we've uh, ended the whole game and found out that actual game outcome was +1, for example. And we also computed the action probabilities using that network. So for each time step, uh, we compute the probability for taking each action. So each action, yeah. So actually the action that was selected, the probability of, so suppose I given this, I selected this action, and I did n dot as 100. So there were many other actions that were also visited. So even they had some value of n. So I will find the probability of taking this action uh, given this state as number of times I visited this state over number of times I visited all other states, all other actions for only this state. Number of times I visited, took all other actions given this state. So that will be the probability of taking this action given this state. So that's what I get. And this will depend on the network and the score. Uh, Sorry, not the score, but yeah, this will be depend on the network. And the actual outcome of the game is +1. So now I'm going to use this to update my network to find the loss between my network and to fix it. So this is the loss function. So let's break it down in two. So this part finds the difference between the v that you computed given each state. So I I selected this as the action, final action after this. So given I took this action, what was my V? That's what I computed here. And what was the actual game score of the game? That's here. And again, this is done from the perspective of the player. So you will understand this when you implement it. Yeah. So because +1 is a good thing if you took odd actions, but it's a bad thing if you took even actions. So +1 is a good score for X, but it should be minus. It's a negative for 0. So it's adjusted here for the perspective. So anyways, so the first term, what it does, it finds how different my estimation of final score was at each time step from the actual times from the actual score. And the second term uh, just looks at the probability of taking this action and given this network. So what we are doing here is when we reduce loss, we want to minimize this because it's a positive term, and we want to increase this because it's a negative term. We will end up doing that when we minimize loss. So we want to minimize the difference between our estimation and the actual game. That's good. And we want to increase this product that uh, increase the probability of selecting this action given this. So suppose the probability of selecting this action uh, was, let's say, zero point 0.7, because it has to be higher because I selected it 0.7. And but this network is not predicting this action. Remember, I selected this action not using the network. I selected this action using U and N, and I was using this network to predict next player's action. That means even this action was predicted here when I chose to put my circle for my agent 2 here. uh, this action would have been predicted during that time, right? So I want to alter my network such that it will predict correct action for the other player. So by increasing this probability, by reducing this and by increasing this probability, I'm changing my network such that it predicts the second action, second agent's action better and better, because this was the optimal action selected because Z was 1. So I want to increase this product and I want to reduce this difference. Okay. So this way I will improve my policy network. I will improve my predict network. And this is the back propagation. Then I run. Now this back propagation is different than what we did, expansion back propagation that I talked about previously. This is for updating the networks. Right. This is just a example that these two things are what we're doing at each state before we select the action. So again, important to note here is that the probability here comes from the actual action that I selected, and not using the network, but using U and N. And I want my policy network to predict the other agent's action better, so that my U will also become better, right? Because the U current U depends on this, which is predicting the action taken by the other agent given this state. If I take this action, what action will the other agent take? That's what this is computing, and this is going into U. So if this is accurate, my U will be accurate, and ultimately my current action taken will also be accurate. So I have to train this. That's what I'm doing here, and this probability comes from U, U, U or N. And once I update this network, here, I make it better and better, my probabilities will also become better and better because my U is going to be better. So I'm improving my critic and improving my policy network here. Critic here computes the total end game score given this state, and this here estimates what the action will be for the other player given this state. Okay, so let's summarize the AlphaZero algorithm. We initialize a network. We just get some random weights. We play full game using MCTS as we saw previously, and we get the actual game score and the probabilities of selecting the action selected. What were the probabilities of the actual actions that we selected at each time steps? Then we compute the loss, and then we reduce this loss by performing gradient descent. And then we again play another game, again compute loss, minimize this, improve the network, and we keep doing this again and again. And thus we update our and improve our critic network and policy network. So that's AlphaZero basic AlphaZero algorithm for you. Of course, there will be many modifications to improve the computation time, to reduce the computation time, make it more efficient, and all those things. There is a lot of material. Even in the lesson, if you see, there are some papers suggested. So these are the original AlphaZero. This is the original AlphaZero paper. I encourage you to read this. Very informative, I should say. Very informative. So you should read this. And it has was by the researchers at DeepMind. Also, I just finished the theory part. You are more than welcome to check out this implementation of AlphaZero on very simple tic-tac-toe game by the instructor of this lesson. Uh, yeah, advanced tic-tac-toe. Try the simple one, and then advanced is having more steps. Sorry, more higher grade. So if you have any questions, of course, you can reach out to me anytime and on Slack, and I will respond to you as soon as possible. So thank you. Thanks for watching this, and have a good day.